The instamatic focal point bringing damage to your burrow. We some brothers from the east with them beats that be thorough. Got the solar gravitation, so...
And welcome to the video on trigonometric limits. Okay, so there are a few key things that we can take from this section, and one of them is called the squeeze theorem. Squeeze theorem. Okay, and what is the squeeze theorem? So, let's see. Formulaically, it says, so according to the formula, so here, or formula, or just the theorem, this is the formal definition of it. If you were to have an L of x, so this is some function that is always below or equal to f of x, which is also below or equal to a u of x. So this is L for lower function, f of x is our middle function, and u of x is our upper function, okay? So like our upper bound, sort of, all right? So if this is true for all x on some interval, we'll just call it AB, okay? Then f of x is basically kind of trapped. So here's a pictorial like diagram of what I'm talking about. So if from A to B, and A could be negative, B could be negative or positive or whatever, just some interval on x, then let's say we have an L of x. Well, okay, so here's our L of x down here, because this is the lower one, right? And then here's our upper function, and here's our f of x. It kind of just rides in the middle there. It can't go above the u of x, and it can't go below the lower L of x, okay? So it's just in the middle there, like I said. Alright, so basically f of x is trapped between, so f of x is trapped between our L of x and u of x, okay? So in a more, not drastic, but I guess a little bit more drastic situation, I'll draw that on the next slide. So what if we were to have something like this? Okay, so we have our x and our y, and here's A, and here's B, okay? So A and B. What if L of x were something like this? Sorry, our u of x, because that's the upper one, right? And then what if our L of x was like this, and it actually came to the same point on this interval here? So it comes to the same point there, and f of x, which has to stay in between these two functions at all times, in between a and b, then that would go something, it has to squeeze in the middle there, so it has to go through that point as well, okay? So again, this lower function is L of x, the middle one is f of x, that's the one we're concerned with, and u of x is the upper function. Okay, so again, I'll state what the theorem is saying. So if L of x is always less than or equal to f of x is always less than or equal to u of x, and this is on our interval a to b, right? And the limit as x goes to c, when c is in, so c is somewhere in here, okay, so c is in, this means contained in, that symbol there is contained in a and b, so that just means it's in between there somewhere, all right? It's either a, b, or somewhere in the middle, okay? So anyways, if limit as x goes to c, so as x goes to some point in this interval a to b of L of x is equal to limit as x goes to c of u of x equals L, some constant L. So at this point, that would be this level here. So that would be the point L on the y-axis. So basically, if the upper function, if the limit of the upper function is the same as the limit of the lower function, so if these two are the same at a given point C, that means that f of x, the one that has to always stay in the middle, is going to be, it's going to be forced or like squeezed into going to the same limit, approaching the same limit, okay? So these are our ifs, and then our conclusion for the theorem is then limit as x approaches c of f of x exists, first of all, that's always important, that the limit exists, and our limit of f of x as x approaches c must equal L as well. That rhymes. So it must equal capital L, okay? So that's the general overview of what the squeeze theorem is. It kind of makes sense. I mean, if you think of it sort of like a sandwich, like your top piece of bread is your u of x, and the bottom piece of bread is the L of x, and whatever's in the middle has to stay in the middle, right? Even if you squeeze it, squeeze the middle down or something with your fingers, the lettuce still has to stay inside, the meat, and or the cheese, if you're a vegetarian, or, okay, I don't know the difference between, yeah, anyways, so the contents of the sandwich are f of x has to stay in between the two slices of bread, okay? So, anyways, the trick, and I'll just go over one more tip here about the squeeze theorem. So, squeeze theorem, you might be wondering, okay, that's great, I understand the whole, squeeze and trapped between two functions thing, but why, how am I even going to do this in a problem? So, the trick is to find, so once you're given, a function, usually you'll be given, an f of x, okay, so our middle one, but we don't know it's the middle one, but we just, the question just asks us to find the limit of blah, blah, blah. So if we're given limit as x approaches c of some blah, 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 what we have to do is find a function above and below, always above, and find a function above and a function below, always below on the given interval, okay? Yours, which is our f of x, okay? So that would be our given. So you can apply the squeeze theorem. Apply the squeeze theorem. Squeeze. Okay, hold on a moment here, almost done. So you can apply the squeeze theorem to find your limit, to force the limit of f of x to be something, to find the limit. Okay, so you don't have to worry about this too much. I'll do an example of this on the practice problems video, okay? So another of the important things to know, so I'll write important, specifically trig, important trig things to know, okay? Alright, so among those, and they have to do with limits, of course. So one thing to note is that the limit as theta, this is our variable now, approaches 0 of sine theta over theta. Whenever you see this, that's going to equal a 1, okay? As well as limit as theta approaches 0 of 1 minus cosine theta over theta. This is not going to equal 1, but it's going to equal 0, okay? Alright, and then also something to note is that cosine theta is always less than or equal to sine theta over theta is less than or equal to 1 for negative pi over 2, negative pi over 2 less than theta less than pi over 2. So basically on the right side of the unit circle, on the right half of the unit circle, given that theta is not equal to 0, then this statement here holds true. So these three things that I've shown you here, so number 1, number 2, and number 3, which includes all of this stuff. So number 3 has these things here. I'll section them off. So number 3 is just that bottom, this whole row here. Number 1 is that first thing, and number 2 is this upper right box. So these are all, they're just takeaway key concepts that you'd be advised to remember, concepts and formulas that you should know. And there are lengthy proofs in the book that lead you to these conclusions, but here I would just say these are key things to know. Key things to know. Okay, so just keep that in mind when you're solving through problems. Sometimes these are just freebies, sort of. Like if you see limit as h approaches 0 of sine h over h, then you're automatically just going to say, oh, okay, that equals 1. And there's no need to go through the entire proof or anything that's in your book. You just say that equals 1 because you recognize it. Okay, so let's do an example. So what we're going to solve is limit as h goes to 0 of, not L, but sine of 2h over an h. Okay, so here, this kind of looks like the one that I just went over, right? I introduced that here, so that was limit as theta approaches 0 of sine theta over theta. That one equals 1. Okay, this is a totally different thing. That's just one of those key concepts that you'd that would help you to know, that would benefit you But anyway, so this is almost there. We have an h here, which could be replaced by a theta, right? We don't have an h there, though. That's a 2h, but we do have this h here. So how do we get something on the top? So we can't really change this 2. We can't just like take it out in front or anything like that, because it's in the sine thing, right? It's in the sine function. But what we can do is make the bottom look exactly like the top there. So if we add a 2 down here, so let's do that. So we have limit as h goes to 0, sine of 2h, right? That 2 is bound to the h inside the sine. But now we have an h down here. So what I'm going to do is add a 2 down here. So that looks exactly like our 2h here. But in adding that 2, I also have to add a 2 on top. So then we have a 2 over 2. And it's like I just multiplied by 1, but in a little different form. 2 over 2. Okay? That's why I added that 2 there. And now what we can do is take this constant, this 2, and I'm going to move it all the way out in front. Okay? Because we can do that due to the constant multiple rule, or the limit law. Remember on our basic limit laws. So now we have a 2 times limit as h approaches 0 of sine of 2h over that same 2h. Okay? And now this looks like the form here, right? We have sine of something over that exact something. Okay? So we can apply our key concept, or our key formula up here, okay, to this part right here. All right? So that kind of comes from our toolbox of knowledge. So we have that 2 just sitting out in front. And then everything in the box we know is equal to a 1. All right? So our final answer is just going to be simply a 2. Okay, so that does it for this concept video. And again, look out for the practice problems video for this same trigonometric limits section, so you can see an example of how we use the squeeze theorem.
Stick a push to make a bundle to escape the math. Man, life can get all up in